In this problem, we're given a heavy disk with a mass of 35 kilograms and a radius of 32 centimeters, and this disk is attached to an electric motor giving us an average power output of 1320 watts. So starting from rest, we're going to turn this motor on for 8.5 seconds. And we have a few questions to answer about the motion of the disk. In parts A and B, we're looking at the angular kinematics of the disk, so we want to get the final angular speed and the average acceleration. And then in part C, we're going to get the average torque exerted by this motor. So to start with the angular speed calculation, the whole idea here is to use energy to approach the problem. We have an average power output of this electric motor, and we're given the amount of time that it's generating this 1320 watt power. So power is the time rate of change of an energy transfer. In other words, all we have to do to get the total energy transferred is take our power and multiply it by how much time is going by. So we plug in our 1320 watts, and we multiply by the amount of time that this motor runs for, which is 8.5 seconds. And this gives us 11,220 joules of energy output. Now that energy is reflected in the rotation speed of the disk. And just note, we're ignoring here as an approximation the moment of inertia of the shaft itself, which should be negligible compared to a gigantic 35 kilogram disk. So the strategy here is to say that this total energy output goes into the final rotational kinetic energy of the disk, which is given by 1/2 I omega squared, where I is the moment of inertia of the disk, and that omega is the final angular speed. So we could just plug the formula for the moment of inertia of a disk into the right-hand side of this equation, but it's actually useful to just separate the calculation of moment of inertia for this particular problem, because we're going to use it again in part C. So the moment of inertia of the disk is 1/2 mr squared. And if you're wondering where that came from, I'll post a link at the top to a video where that was derived using a physical integral. And we go ahead and sub in the mass of the disk, that's 35 kilograms, and the radius, 32 centimeters, which I'm going to write as 0.32 meters. And we need to square that. And we get about 1.792 kilogram meters squared for that moment of inertia. So back to our plan to find the final angular speed of this disk. We know the energy that was pumped into the rotation of this disk, that's 11,220 joules, and that's equal to 1/2 times the moment of inertia, which we now know is 1.792 kilogram meters squared, times the final angular speed squared. So we just take our 11,220, multiply by 2, divide by 1.792, and square root the result, and we have our final angular speed. Into 3 significant digits, this gives us 112 radians per second. Now in part B, we want to compute the average angular acceleration of the disk. So we're just averaging over the total motion here and saying that our average angular acceleration should be given by the change in angular velocity divided by the change in time. So we started from rest, and our change in angular velocity is just the result we got from part A. We went from 0 to 112 radians per second, and this took 8.5 seconds to accomplish. So we end up with 13.2 radians per second squared for our average angular acceleration. And a more intuitive way to say that is 13.2 radians per second per second. In other words, the disk is speeding up on average by 13.2 radians per second every time 1 second goes by. Okay, now that we have the average angular acceleration of the disk, we can get into part C, where we're asked to compute the average torque exerted by this motor. So when we observe an angular acceleration, we know there must be a torque on this object causing that increase in its rotational speed. And the relationship between torque and angular acceleration is given by tau equals I alpha. And here we're talking about average values. So I have an average angular acceleration, and that's connected to an average torque exerted by the motor. And this is where it pays off that we separated the calculation of moment of inertia in part A. We already have the moment of inertia, so that's 1.792 kilogram meters squared. And we have our average angular acceleration from part B, that's 13.2 radians per second squared. And I kept full precision in my calculator throughout this entire calculation. So we end up with 23.6 Newton meters for the torque. Now, if you used the previously rounded numbers in your final calculation, you probably got 23.7 Newton meters, but that's fine. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.